Welcome. Now we shall learn about another processing methods related to the removal of the acid gases, and this lecture will be divided into a few parts. First we shall see in this particular lecture that what are the various types of removal methods of the acid gases, and then we shall see the various criteria to see these to choose these methods, and then we shall be focusing on the absorptive acid gas removal. So, first let us see what are the acid gases in natural gas. They are carbon dioxide and hydrogen sulfide. Now, why do we need to remove hydrogen sulfide? Because it forms weak corrosive acid in presence of water. It is very toxic, and though it can be detected easily at low concentrations because it gives a rotten smell, but at high concentration it numbs our olfactory system. Olfactory means that our smelling system is affected, so that we cannot smell it that at high concentration, and when we cannot smell it, but it is going inside our system, and then it can prove lethal to us. So, it may cause death for concentrations more than 1000 ppmv, and the threshold limit is a prolonged exposure is 10 ppmv. For long exposure, at as low as 10 ppmv of this H2S can cause death. Then for high concentrations, what happens? This H2S can form other foul smelling sulfur compounds like carbon disulfide, mercaptans and sulfides. Why we need to remove carbon dioxide? Because it again forms weak corrosive acid in presence of water like H2S, and it is non-flammable, and that is how it reduces the heating value of the natural gas. So, for these reasons we need to remove these two gases, and here in this table we find the maximum limit, permissible limit in this natural gas. For transportation in a pipeline or used for residential and industrial fuel, we find that the carbon dioxide should be less than 3 to 4 mole%, whereas H2S concentration should be less than 6 milligram per cubic meter. Whereas for cryogenic plants in which we are handling LNG, that is liquefied natural gas, liquefied LPG, liquefied petroleum gas, and the NGL, that is natural gas liquid. So, in these cases we find that these are the maximum limits which are permissible in these gases. Now, when we talk of this acid gas disposal, how we can dispose of carbon dioxide? That we can dispose it by injecting in an enhanced oil recovery system, and this is the method to recover any residual petroleum oil which are entrapped in the rock formation in the sediment. So, there we can use carbon dioxide, because it is important for us not only to capture the carbon dioxide, but also to find out a way so that it can be sequestered. So, this is one of the ways, and another way is to vent out to the atmosphere if the concentration does not exceed the environmental regulatory limit. Then similarly for H2S gas, we have incineration, that is burning and venting to meet the environmental regulations, or we can react it with H2S scavengers, that means like iron sponge, then this can react with the H2S, and then we shall be learning more about them later. Then we have this conversion of the elemental sulfur by use of the Claus process, and then we can inject these sulfur compounds in some underground formation. Now, let us see the various basis of this removal of these acid gases. We may remove carbon dioxide from a gas that contains no H2S, or we can remove H2S from a gas which does not contain carbon dioxide, that is carbon dioxide and H2S are present alone, and then we can simultaneously remove these two gases, or we can selectively remove H2S from a gas containing both CO2 and H2S. Depending on the requirement, we will have to adopt suitable method to meet these conditions. Now, there are various bases of the gas separation. In this case, either we go to molecular properties like kinetic diameter, polarizability, then thermodynamic properties like vapor pressure, boiling point, solubility, then transport property like diffusivity, adsorption property. So, all these properties will dictate that which type of method we have to adopt for a given application. So, here are the various methods: absorption, adsorption, membrane separation, thermodynamic phase change, and chemical conversion to another compound, and in this particular lecture we shall be focusing on absorption. Now, first before that let us see what are the criteria to choose these acid gas removal methods. One is this, the type and the concentration of the impurities, that is how much amount of H2S and CO2 are present, then temperature and pressure of the sour gas, and then outlet gas specification, the volume of the gas to be processed, the how much selectivity we want for the acid gas removal, then the specification of the residual gas, acid gas and liquid products, then the cost of the process, in any environmental constraints, and size and weight of the separating units in case we are talking of offshore application, and in this case carbon dioxide removal is done offshore, but H2S is not generally removed to avoid problems of the handling the elemental sulfur on the offshore applications. Now, let us come to the absorptive acid gas removal. Here we find from this diagram a typical arrangement to remove these gases by absorption. Here we have an absorption column and we are feeding the gas from the bottom, and the solvent, some solvent is fed from the top, it comes down and it moves up, and they are mixing counter currently in this particular column, and during this mixing what is happening, the carbon dioxide and H2S are getting dissolved in the solvent and they are removed from the gas. The gas which is coming out will be having now less amount of these gases, whereas this solvent will be rich with the H2S and CO2. So, that is how a typical absorption process looks like, and we have various types of absorption processes which are physical, that means without any kind of reaction, then chemical, this is with reaction, and hybrid, which includes both physical and chemical absorption process. First we come to the physical absorption. Here we have the solvents used here, that Selexol, these are the Selexol, Rectisol and Purisol, they are the names of the commercial names, and they are basically all these compounds chemistry wise, and their compositions are proprietary, that is why they have been given some commercial names. And similarly for the chemical absorption, we have this, basically they are amine based, we have primary amine, secondary amine, tertiary amine and mixed amine, and here are the names of some of these amines. Now, if we compare the physical and the chemical solvents, we find that the physical solvents have low energy requirement for solvent regeneration, because the H2S and CO2 are weakly held by the solvent, whereas the energy requirement for the chemical solvents is high, because a much stronger bond due to the chemical reaction between H2S, CO2 and the solvent. Then this selective between CO2 and H2S, whereas in chemical solvent they are not selective between these two gases, that means these two gases are absorbed almost to the same extent. Then physical solvents are very sensitive to acid gas partial pressure, whereas chemical solvents are relatively insensitive to the partial pressure of the acid gases, that means the concentration of the acid gases in the feed mixture. Physical solvents are cheaper, chemical solvents are costlier, then physical solvents are less susceptible to the impurities in the gas stream, whereas chemical solvents are more susceptible to the presence of the impurities, because the impurities again may get reacted with these solvents and they will reduce the solvent capacity. And then we have limited extent of the acid gas removal, whereas in case of chemical solvent they can reduce the amount, this acid gas, to a very low extent, and even they can go to ppm level. Next we come to a typical physical absorption unit. in this we find that we have the soured feed gas here, which is fed from the bottom of the absorption column, and from the top we are inputting the lean solvent. Lean means this solvent does not have much of carbon dioxide and H2S. If it is fresh solvent, it does not have any, but if it is regenerated, the amount of carbon dioxide and CO2 and H2S will be less. So, this is why it is called lean solvent, and when it contacts with the upgoing gas, then what happens? It takes up the carbon dioxide and H2S, and that is how it becomes a rich solvent, and then it is flashed twice at two different pressures, and because of flashing only, and flashing does not take much energy. So, because it's flashing, we can do a multiple cascaded flashing, high pressure, medium pressure, low pressure, and by reducing the pressure we are able to recover the solvent more and more. So, just by flashing we recover the these gases, and from then we take the solvent back to the column after regeneration. So, this cycle is continued until unless we find that the capacity of the solvent has not come below the requisite capacity. So, this is quite simple, and but in case of the chemical solvent we need more elaborate arrangement for the regeneration, because the bonding between the solvent and the acid gases are much stronger. In this case simple flashing does not work. So, in this case what happens? The regeneration is done by steam stripping. That means we put the steam, and this steam again it is a external heating we do to get the steam, and this steam is put in another column, regenerator column, and in this regenerator column we take the rich amine, rich solvent from the top and steam from the bottom, and then we get this this particular amine from this column, and it is sent back to the actual absorption column. So, this is how we are operating the chemical absorption unit, and here we are needing the steam and not simple flash. And then we have mixed hybrid or mixed or hybrid solvent and why we use this? Because they are having the combining the good effects of both the physical and chemical absorption processes, which we shall see just a while later. And then we have they are suitable for acid gas partial pressure in natural gas more than 100 kilopascal, and these are the various mixed solvents used. Sulfonyl D is something like a DIPA and sulfolane, sulfonyl M is MDEA and sulfolane, and so on and so forth. So, we are using different types of mixed amines, and these are the applicability of solvents. The advantages are that their high solubility at low carbon dioxide partial pressure, their low energy consumption for regenerating the solvent, and they have very high capacity to remove the acid gases. They do not foam much, and they have very low corrosion tendency. Disadvantage are that there will be high hydrocarbon loss to the solvent than the conventional amine processes. And here in this particular figure we find that we are listing the various types of solvents used for the acid gas removal. In this we have chemical solvent, we have primary amine, secondary amine, tertiary amine, and others like these are not amine. Potassium carbonate is not an amine. These are the various chemical solvents, and these are the physical solvents, Selexol, Rectisol, Purisol, and others. All these things are given the commercial names. And then we have the mixed solvents like sulfinol D, sulfinol M, Flexsorb, Amisol, etc. Now, advantages of the whole absorptive acid gas removal in comparison to the other processes like adsorption, membrane, etc., that we find that they are most efficient for high partial pressure of the acid gases. That means, if the acid gases amount come down, they may not be that economical, and they absorb very high heavy hydrocarbons, that they can remove the low concentration of heavier hydrocarbons, and they can selectively remove the sulfur compounds, so that we can separate carbon dioxide easily and cost effectively, and they can work at near ambient temperature. However, the disadvantages are that we have to spend energy for the solvent regeneration, and they have low absorption capacity that leads to high solvent circulation rate and large equipment size. Now here are the comparison of the carbon dioxide and H2S removal processes using the various solvents here. We find that the various solvents we are putting in terms of the capability of meeting the H2S specification, whether they can remove these sulfur compounds or not, and how selective are they about the H2S removal, and the minimum amount of CO2 level that can be obtained. And in this way we find that the various kinds of solvents are capable of removing sulfur to different extents and sulfur compounds, and we find that the minimum amount of carbon dioxide level reached by this solvent also differ. And here it continues with the other solvents here. So you can find more detail about these processes from these references. Thank you.